Welcome to the demonstration corner. Today we're going to talk about the power of short test times that are available on the MP-1 for the Transient Plane Source Method, and really how that ties into if you're measuring very small materials of a low to medium conductivity or small materials that are very conductive, how critical that is. But before we do, as tradition here in the demonstration corner, we're going to turn the camera around and just talk about the different methods. So here is our guarded heat flow meter for measuring complex materials, whether they are heterogeneous or non-repeating composites through the thickness. So that means that through the thickness, the layering structure or the anisotropy is non-repeating. Those are both critical reasons why you'd want to use ASTM E1530 guarded heat flow meter. This has a temperature range of -20 to 310 Celsius. ASTM C518, as well as the ISO equivalents for measuring construction materials and insulation. We have two different sizes and two different temperature ranges. This is our HFM 100, which is 12 inch by 12 inch or 300 by 300 and up to 100 millimeters thick. Our two temperature ranges are -20 to 75 plate temperature and -30 to 110 Celsius. I encourage you, if you're interested in this method, we have a demonstration video and more information on our website about the other models. We will be talking with the MP-1, of course, but this is our MPV, which is the new addition to the measurement platform series. MP stands for measurement platform. This combines two primary methods for measuring thermal conductivity, thermal diffusivity, and specific heat. One is the transient plane source, following ISO 2207 for solids, pastes, and powders, and ASTM 7896, sorry about that. ASTM 7896 for measuring liquids and phase change materials. So this is, we've introduced this as a mid-level instrument for combining those two primary methods as well as a few other methods to extend the use of it. Our transient hot wire, this is a focused instrument for measuring thermal conductivity, thermal diffusivity, and specific heat for liquids and phase change materials, with the ability to back pressure up to 20 or 35 bar, which allows you to test past boiling points of liquids. This has an integrated temperature platform, which this one is 10 to 200 degrees Celsius, but overall they can be packaged from -160 to 300 Celsius. This is following the same additional methods available on the MP series 7896, so ASTM D7896. This is our small format insulation following ASTM C518, so a small format heat flow meter for measuring small types of insulation. It's quite ideal when you're looking for measuring thermal resistivity for a high porosity or heterogeneous material. Our MP2, which is our entry-level measurement platform system, this combines several primary sensors that are available for measuring solids by transient plane source, liquids by transient hot wire, and soil and polymers by transient line source. Very good instrument, measures absolute values, meaning no calibrations or factory or user calibrations required. So we have lots of demonstration videos on that. So the MP-1, which is our marquee or really the industry leader in transient measurements, we've brought together two primary methods, again like the MPV but at an advanced level, the MP-1 being our most important instrument, following really having the widest ranges of all the different specifications. Our MP-1 itself controller comes with a 4-channel switch with smart software that allows you to use all of those in a nice, elegant, balanced way to maximize the throughput capability. So it's like having 4 instruments side by side but only one controller and the correct software to make that all work. Temperature platforms that you can add to each method, again, transient plane source and transient hot wire, and the temperature ranges of these are available on the website. The transient plane source, all the measurements I'm talking about today can be done at room temperature as well as inside of a temperature platform, and we recently did a demonstration on the temperature platform and how it set samples up and the different test cells that are available for it, as well as the temperature range that is available and the options on it. This one, as it sits here, is our basic, and it's 0 to 300 Celsius. It does not require any external cooling. but it can be extended down to cryogenic. And that can plug into the same controller as well as any other method or module, and room temperature for doing high volume. So these are the two primary types of sensors and methods you can combine with the MP-1. Additionally, you can add transient hot strip and transient line source. Those have specialty applications, which if you're interested, let us know. We will be doing demonstrations on those as well in the future. So if you bring the camera in, what we're going to talk a little bit about is the importance of variability in test time, both short and long, but today our focus is on short test times. So these look like big samples, but these are copper. These have an approximate thermal diffusivity of around 116 or 17 millimeters squared per second. And even though these are large in size, these are about 35 millimeters in diameter, and the sensor that we would propose to use in this example is 6.4 millimeters diameter, or 3.2 millimeters radius. That leaves what looks like quite a bit of penetration depth. But if you were to look at a measurement, you would see that we need a test time of 0.25 seconds to keep the heat within the boundaries of the sample based off the really high diffusivity of these materials. So even though these are large in size, because they have a very high diffusivity, and we do have various sensor sizes which give you different ranges of penetration depth. Penetration depth being described as the distance from the edge of the sensor to the edge of the sample when it's centered. So this very critical to be able to measure 0.25 seconds to keep the heat within the boundaries of the sample, which is critical to the basic theory of transient plane source, that sample being a semi-infinite body. So another opposite end of the thermal conductivity range, so these are around 400 watts per Kelvin. Opposite end of the thermal conductivity range, this is Macor, small pieces of Macor, which are around 1.5 watts per meter Kelvin and around 0.7 millimeters squared per second for diffusivity. These are 5 millimeters square by approximately 1.5 millimeters thick, so very small on the lower side of thermal conductivity. And this is measured with bulk module, what I described, and we're measuring this with the bulk module. So we have demonstration videos on all these individually, so I invite you to look at them, but collectively what I wanted to describe was the importance of short test time. So on Macor, based off the diffusivity, the test times that one could use on the MP-1 are 0.25 seconds to 0.5 seconds. So again, another example of even when you don't have high conductivity or high diffusivity, the importance of variable test time, even when just due to the physical size. So the smallest dimension there, in terms of from the edge of the sensor to the edge of the sample or the thickness, is the thickness, 1.5 millimeters thick. This is a 4 millimeter or 2 millimeter sensor. So these are bulk, and what these are examples of measuring highly conductive materials by the slab module. So we have a demonstration on the slab module, and we will be doing a demonstration on these specific samples. These are all aluminum from 30 millimeters, 25 millimeters diameter, 19.2 millimeters, and 12.7 millimeters or half-inch diameter, and they're all 1.3 millimeters thick. So what we did to sort of really emphasize the importance of test time is we measured each of these with the slab module, and in the slab module, the penetration depth is from the edge of the sensor to the edge of the sample in that in-plane direction. So with the slab module, we're isolating the thickness and looking at the penetration depth from the edge of the sensor to the edge of the sample. So on the smallest sample, that's a very small penetration depth. I think that's, I could calculate in a sec when I get back to the computer, but it's a very small penetration depth, and the test time is very small. So you'll see on this example when we share the data that we essentially did 0.25 seconds measurements on all of them to stay within the boundaries of the sample, because aluminum has a pretty high diffusivity, but we were able to take our 0.25 second measurement and chop it down any further. So at 0.25 seconds, we're measuring or collecting 600 data points. So by removing points off the back of a 600 point or 0.25 second measurement, we can reduce the penetration depth. So what you'll see from the example here is that although we're doing 0.25 seconds across all of them, ultimately, to keep the heat within the boundaries of this 12.7 millimeter diameter, we had to chop the data down to 0.11 seconds. And that still gave us 200 data points. So we lead the industry in a collection of high number of points. And when we're asked the question, why is that important? It's for examples like this, so that when we want to chop our shortest test time, and the shortest test time on the MP-1 by Transient Plane Source Method is 0.25 seconds. In fact, the ranges are 0.25 seconds, 0.5 seconds, 1 second, 2 seconds, etc. But on the shortest time, while we're collecting 600 points, you can see the advantage of that because we can measure such a material with a high diffusivity. That's a very difficult measurement if you're not collecting a high number of points like we are. And you'll see that example when I share the software and the data we've measured. Lastly, so we have bulk, description of larger materials but very high diffusivity, small samples of dimension but on the lower side of diffusivity, slab, which are designed for conductive sheets, metals, and type materials that are thinner and radial direction larger. You can see the advantage of it here. So the last module to really emphasize is the one-dimensional module. So this is NIST 8420, which is electrolytic iron. This is around 6.5 or 6.6 millimeters in diameter and about 10 millimeters in height. That's the perfect configuration for one-dimensional. And again, there's a demonstration video on this exact application. The test setup would be you would place that sample in contact with the sensor that has the closest diameter to it. And this has a conductivity of around 75 or 77 watts per Kelvin. Our test time on this is 1 second. And that test time, in this case, we're looking at the penetration along the length of the rod. So in 1D, it's along the length of the rod, whether it's symmetric or asymmetric. Slab, it's along the in-plane direction of the isolated direction, which is in plane. We're isolating the thickness, sorry. And on bulk, it's all directions. So in this case, it's the smallest dimension from the edge of the sensor to the edge of the sample, both considering thickness as well as when the sensor is centered. So that's a little discussion on the importance of test time. Of course, in here, we are taking advantage of variable sensor sizes. The bulk one here, the sensor size we're using, is 0.88 millimeters diameter. That satisfies the test requirements. And for each of these, the ITPS, which is our intelligent design on our MP-1 software, but after you enter the name of your sample and your dimensions, it automatically recommends what is the most appropriate sensor and test time for each of these variations. But when you're considering an instrument and your application, please do consider test time as it's very important to following the theory. And that theory can't be changed. It can't be modified. If these have to be considered semi-infinite bodies, the heat has to stay within the dimensions of the sample. So now I'm going to switch to the desktop and just show briefly that same NIST slab and the importance of time. So 0.25 second measurement. Here's 5 measurements. We have inputted the volumetric specific heat of aluminum. When you're down around these test times, you need that to correct for the diffusivity properties. Our thermal conductivity is 173, and you can see the importance of that. And our calculation window is the full 0.25 seconds. That's what N means. It means all the data is included. In our 0.25 seconds, that first set of data was on the 25 millimeter disc. This second set of data is on the 19.2 millimeter disc. And again, we've inputted volumetric specific heat. You can see our conductivity. Our repeatability suffers a little bit because it's a very short time. In this example, we're calculating down to a 0.15 seconds, which still represents a large number of points. So if we look at the residual pattern, after chopping this down, you can see it's still a large number of points, actually over 200 points, because again, we're collecting 600 across 0.25 seconds. And then our last example, which is 12.7 millimeters diameter. You can see the residual pattern. We still have over 200 points. and our bulk properties. Now, of course, we do have some effects of repeatability because we're selecting such a small portion of time, but that average is still well within the expected value. Just the percent repeatability suffers a little bit from taking so few data points, but you still have a relatively acceptable value. So that, and again, that's a selection of points down to 0.11 second. So that gives you an example of using the same time and the power of being able to chop points from the back of a 0.25 second test to simulate shorter test times, all the way down in this example to 0.1 second, and still be able to make measurements at that full scale. So of course there's a wide variance of test times, but hopefully this is one good example of the importance of test times and what it means to the flexibility of your instrument. So again, the MP-1, just commenting a little bit on the MP-1, our conductivity range that we describe for the transient plane source method is 0.005. Of course, that would be on isotropic and anisotropic material. And time scales at those diffusivities and conductivities are very long, based off dimensions. And on the higher scale, it's 2,000 watts per Kelvin. And of course, at those higher scales, the test time requirement to measure them and the flexibility of that test time and sensor size is really critical. So the test time that's available on the TPS are 0.25 seconds, 0.5, 1 second, etc., all the way up to 2,560 seconds. And on those shorter test times, our high rate of data point collection is a big advantage when you need to chop down to an even shorter test time. So even if you're making a 0.1 second measurement by another transient plane source method, if you're not collecting high enough points, that's actually still not equivalent to a 0.25 second measurement at 600 points, and all those points being highly reliable and robust. I think that covers everything I want to talk about. Again, we will have, we do have a demo video, so in the description there'll be a link to this demonstration video. There is a demonstration video for this Maycore and this measurement. We will be doing a demonstration next week on these discs of aluminum and setup and sharing of data in more depth, and in the future a copper of the same nature. So we'll make sure what is available is actually in the description, and thank you for joining us. Appreciate the time.